Okay, everyone, so we're talking about resonance structures. We are starting on page 34, and we practiced this actually a little bit in class. So, O3, 3 oxygens. I'm going to put oxygen in the middle. And actually, when I do Lewis dot structures, pencils are great because I know that I'm like erasing and moving electrons. And so then I'm going to start with single bonds to the other oxygens. Based on oxygen's location, we got 6 valence electrons. Okay, so notice we have this extra electron there. Why don't we? And remember on the middle, so this oxygen is using 2 of its 6. So then we'd go 4 and 6, okay? But what if I take one of those electrons and one of those electrons and I turn it into a double bond? And then I take this electron and this electron, and then I could turn it into a double bond right there. That's one option. It gives us an expanded octet in the middle. 2, 4, 6, 8, 10. So another way that this could have looked is, I'm going to go back to, I had one here. This was a double bond. Okay. And then the other side was a single bond. How about instead of turning those into a bonded pair, what if we make them a lone pair? Right there. Now the octet rule is satisfied for all of the oxygens, but this single bond and this double bond, why did we choose this side for the double bond and that side for the single bond? They're both oxygen. Could I have switched it? Could I have done the double bond on this side and the single bond on that side? These are all valid Lewis dot structures. Now this one I would say may be bordering on invalid because oxygen is in period 2, and we know period 2 elements don't like to form expanded octets, and so I might not consider that one to be a valid structure, but these two certainly are valid structures. And so those are resonance structures of each other. 2 Lewis dot structures, both obey the octet rule or have validity to them. And in this case, they would show up equally out in nature, but there are times when resonance structures don't occur in equal amounts in nature, and we can find which one is more stable or which one's more likely to occur. Okay? And so CO3, 2 minus, NO2 minus, we're actually going to save these ones, and we'll do those 2 together in class as like a quick little reminder. Okay, so we're going to do resonance structures for those. Let's try this one. Sulfur dioxide, SO2. So nature tends towards symmetry. I'm going to put sulfur in the middle. I'm going to add the oxygens. Oxygens have 6 valence electrons, and right now they're only using 1 of those 6. So similar to before, I can just see what I'm starting with. The name of an electron all by itself, like this, not in a pair, a bonded pair or a lone pair, is called a free radical. And they are unstable. They don't occur very often. So rarely do we leave these like unpaired like this. And sulfur also has 6. Oh, so this is just so similar to what we just did earlier. where we saw that we had two structures that worked really well. So I'm erasing 2 electrons right now. One of them I'm going to put over here with this one. And then the other electron I'm going to put right there. And again, why did I choose that side? Well, it didn't really matter which one I chose. So we have 2 really valid Lewis dot structures here, where the double bond could have been on this side or the other side. And then we have a lone pair on the middle. Okay. This is similar, very similar to the last one, where both of them are valid structures and they would both occur equally in nature. But now I'm going to show you an example of one that it has resonance structures, but one is more stable. One occurs more readily in nature. So look at SCN. And I want you to try something. I want you to give this Lewis dot structure a go. You can pause the video and then try to do it yourself, and then come back and we'll check and see if we get the same thing. Carbons like to be in the middle. I'm going to start with single bonds to my nitrogen and my sulfur. Nitrogens have 5 valence electrons and it's only using 1 of its 5. Carbons have 4 and it's only using 2. Sulfurs, those ones have 6, and right now it's only using 1. Okay, so, oh, I'm missing a charge, aren't I? Let me think. I think this was supposed to be SCN minus. Yeah, okay. Will you guys update that? SCN, but then it's going to be a polyatomic. It's going to be an ion. So we're going to do a -1. So we're going to add 1 more electron. I'm going to put that right here. Okay. So what I have going on right now is right here I have 2, 4, 6, 8. So this sulfur is good. And then on this side, I have 2, 4, 6. Okay. And so, oh, we don't have an octet yet. And what about this one? 2, 4, 6. Oh, that one doesn't have an octet either. So what if I take this lone pair here? And I turn that into a bonded pair. And I'm going to write down this original structure so I can reference back to it. So I had, and this is a good idea before we start making double bonds and maybe triple bonds. This is like what I'm working off of. Okay, so I could do a double bond there, and so that helped the nitrogen 2, 4, 6, 8. Oh, but it didn't, the carbon's still 2, 4, 6. So what if I take this lone pair and I turn that into a bonded pair? So now what happened is this carbon has 2, 4, 6, 8, and this nitrogen feels like it has 2, 4, 6, 8, and the sulfur does as well. So that's a great Lewis dot structure for this. But what if I started pulling from the other side instead of this side? So like this original structure again. Okay, now I know that I have a suboctet here, 2, 4, 6. And so what if I erase this lone pair and I turn it into a bonding pair? Because now, look at the sulfur, 2, 4, 6, 8. And the carbon, 2, 4, 6, 8. Oh, but the nitrogen, 2, 4, 6. Okay? We can sit and we can play with this, but we're going to end up flipping this around, where we're going to have a lone pair that's going to become a bonded pair. And then this lone pair is going to move over there. It's like, is the triple bond with the sulfur, or was the triple bond with the nitrogen? Like, electrons move around, and so it's like, where is this going to settle where it's got a triple bond and a single bond? So these are Lewis dot structures, and they're both valid. Another way that this one could happen is, what if we had double bonds on both sides? Right? Where we would have, we'd have an octet on the middle, 2, 4, 6, 8. We'd have sulfur, 2, 4, 6, 8. Nitrogen, 2, 4, 6, 8. So those are all valid structures. This is an ion, so let's put brackets around these. And then we're going to put a -1 charge. Okay. One of these structures is way more common in nature, which we can kind of glean that it's more stable, more likely to occur. And I'm going to use this technique called formal charge. Now, let me be clear. Formal charge does not mean that these atoms have these charges. It's just a way of me determining which one is the most stable, right? Which molecule structure is the most stable. The way that I get formal charge is I am going to be comparing the number of valence electrons this neutral atom has compared to how many it feels like it has now. So this is what I mean. Sulfur. Right here, sulfur. Sulfur is in group 16, so it feels like it has 6 valence electrons. Okay? Sulfur has 6 valence electrons, but in this structure, right now, it is assigned 1, 2, 3, 4, 5, 6, 7. So that is one more than it would normally have. One more negative electron than it would normally have. So this has a formal charge of -1. Okay, now let's look at carbon. Carbon has 4 valence electrons normally when a neutral atom. And how many valence electrons are assigned to carbon right now? 1, 2, 3, 4. Because remember, it's sharing this valence electron, sulfur sharing 1. So 1, 2, 3, 4. Okay, so its neutral atom has 4, and right now it has 4 valence electrons assigned to it. So that would be a formal charge of 0. There's not any more than there should be or less than there should be. Okay? Nitrogen, when it's neutral, has 5 valence electrons. And this nitrogen has 1, 2, 3, 4, 5. Oh, 5 and 5. So that has a formal charge of 0. Something cool that happens, especially with ions, is if you add up the formal charges, they need to equal the charge of this molecule. Okay? So if it was a neutral molecule, the formal charges need to add up to be 0. Okay, let's do this again. Sulfur. Sulfur has 6 valence electrons when it's neutral. Right now in this molecule, it's assigned 1, 2, 3, 4, 5. So when it's neutral, it has 6, but this is 1 less than its neutral atom. And so if we are down 1 negative electron, that means that its formal charge is +1. Carbon is at 0 because its neutral atom has 4 valence electrons, and right now this carbon is assigned 1, 2, 3, 4 valence electrons. Nitrogen, its neutral atom has 5 valence electrons, and right now this nitrogen atom has been assigned 1, 2, 3, 4, 5, 6, 7 valence electrons. 2 more negative electrons than its neutral form, and so that would be -2. So if I take +1, +0, plus a -2, we get a -1. Okay, our last structure. Try this, hit pause, try this on your own, assign the formal charges, and then let's see if we get the same thing. I got a 0 for sulfur, a 0 for carbon, and a -1 for nitrogen. Okay. The rule of thumb for formal charge. We want to be as close as we can be to a 0 formal charge. So right now, this middle structure is very unlikely to form. We are not going to find much of that out in nature. The first structure had a -1, a 0, and a 0. The third structure had a -1, a 0, and a 0. When we run into this scenario, the atom that is more electronegative has a greater chance of having the negative charge. So this -1 formal charge is either going to be with the sulfur or it's going to be with the nitrogen. Here's nitrogen, here's sulfur. Ooh, I can't really tell. Let me look at my electronegativity table. Nitrogen has an electronegativity of 3.04. Sulfur only has an electronegativity of 2.58. By the way, this is on page 7 that I was looking at. So nitrogen has a greater electronegativity. Okay, cool. And so for that reason, the most likely resonance structure to occur in nature for SCN minus is this one. Less likely to be this one. The reason why is because both of them had a -1 formal charge on an atom, and since nitrogen was more electronegative, it would be more stable having the negative assigned to it. Okay, formal charge and resonance structures, that's not easy. We definitely are going to have to get some practice in on this. I flipped the page, I'm on page 36, and I've already drawn the Lewis dot structures, okay? We already got those. And so we're going to decide which of these 3 structures are the most likely to occur, are the most stable out in nature. Nitrogen, when it's neutral, it has 5 valence electrons, but right now this nitrogen has been assigned 1, 2, 3, 4, 5, 7 valence electrons. So its formal charge, it has 2 more electrons than its neutral form. Carbon has, when it's neutral, it has 4 valence electrons, and this carbon, it has 1, 2, 3, 4, so that'd be 0. Oxygen, neutral oxygen atoms have 6 valence electrons. This oxygen is currently with 1, 2, 3, 4, 5 valence electrons. So it has 1 less than its neutral form, so that would be a +1 formal charge. Try the other 2 and hit pause, see if we get the same thing. Okay. I got, on my second structure, a -1 for the formal charge of nitrogen, and the other ones were 0. And then on my third structure, I got a 0 formal charge for nitrogen and oxygen, and a -1 for the other, or sorry, a 0 formal charge for nitrogen and carbon, and a -1 for oxygen. Okay. Right away, I want formal charges that are as close to 0 as we can be. So because there was a -2 on this one, this structure is not a very stable Lewis dot structure for this molecule. So now I got to decide between these two, which one is more stable. So the -1 can either be with nitrogen or with oxygen. Now remember, electronegativity is biggest with fluorine. So going this direction, oxygen has a greater electronegativity than nitrogen does. So since oxygen has the greater electronegativity, it's more stable. The resonance structure is more stable when the -1 is assigned to the more electronegative oxygen compared to the nitrogen. So this is the best, most stable structure. Alrighty. I'm just looking at some other examples here. This is the concept that we're going to be covering with those resonance structures. I just want to do one more together and then we will be done. Okay. Look at CO2, carbon dioxide. I'm going to put carbon in the middle. I'm going to start with single bonds to my oxygens. Oxygens have 6 valence electrons. So there's its 6. 1, 2, 3, 4, 5, and then 6. Carbons have 4. We can pair them right away, or we can keep them separated. Maybe this one just to show you where the bonds are happening. We could separate them. Okay. This one and that one could come together and form a double bond. And this one could come together and form a double bond on the other side. That's a great Lewis dot structure. Now, there are resonance of this. So another way of doing resonance is just moving around the bonded electrons and the lone pairs. Okay. So what if I'm going to move one of the bonds over here and then one of the lone pairs over there? So that would mean that we get a triple bond, carbon, single bond. We know nature tends towards symmetry, so that's probably not going to happen, but we'll use formal charge to prove that. And then, why did the triple bond go on that side? Why not on that side? So I could flip it around. Those are the 3 resonance structures that I can easily see for carbon dioxide. Okay. Formal charges, though. Notice this. Oxygen, when it's neutral, has 6 valence electrons, and this oxygen has been assigned 1, 2, 3, 4, 5, 6. So its formal charge is 0 because it has the same amount of valence electrons as a neutral oxygen atom. So that's true over here as well. Carbon, when it's neutral, has 4 valence electrons, and this carbon has been assigned 1, 2, 3, 4. So it has a formal charge of 0. On this side, this oxygen has been assigned 1, 2, 3, 4, 5 electrons, but in its neutral form, it would have 6. So there's 1 less negative electron. So that means it has a formal charge of +1, 0, and this is going to be a -1 because this oxygen has 1, 2, 3, 4, 5, 6, 7 valence electrons. And then we get the inverse over here. Okay. When formal charges are as close to 0 as they can be, then that's the most stable. So I got these pluses and minuses, but guess what? There was a structure where they were all 0, so that is definitely the one that is the most stable and occurs in nature. Okay, we'll get lots of practice with this in class. Thank you guys so much for your hard work, and have a wonderful day.